So as a quick review, we talked about the different forms of energy. So the first one is work of a constant force. So this is simply work, or U, is equal to F times S. So force times a distance. The key with this one being that the force must be parallel to that displacement. So, for example, we see on this slide that a force is being applied to the right, and as a result the block moves to the right, and so that force times the distance works. If instead we had a force at an angle, we would only be able to use the force in the x direction times that displacement, because the x direction force would be the only one that is parallel to that displacement. Okay, so that's what's really key with that one. Here are a summary of some of the other terms we talked about. So PE, potential energy, and KE, kinetic energy, as well as heat. And last but not least, which I don't have on this slide, is the work done by a spring. And that would be shown here on this slide, work of a linear variable force. So in this case, U, down at the bottom of the slide, U is equal to 1/2 kx squared. Okay, for potential energy, it's really the same as our equation for work. Equation for work is force times the distance, so potential energy is force times the distance, but we've changed it a little bit. Instead of just F times S, it's W times H, because the force for potential energy would be simply the weight of the object, and height is the distance from some sort of baseline, right? So for example, I think I talked about a ball before being dropped, say from my hand, so the distance at which my hand is above the ground. Or another example would be throwing the ball up from my hand, where my hand is the baseline and the ball travels a height going up. So as the object moves upwards, it has a higher potential energy. As it moves downwards, it has a lower potential energy. Energy, or kinetic energy, down at the bottom here, we see it is equal to 1/2 m, not just v squared, but v1 squared minus v naught squared. So a final velocity minus an initial velocity, each of those terms squared. Okay. So this is the slide that I want you to go back to really, this is gonna, I always want you to go back to this slide to help reinforce what I'm going to be talking about in these practice problems for this chapter. What we want to do is we want to take the initial energy and equal it to the total final energy. So what it really means is we have an initial state and we have a final state. Okay, in the initial state, you might have, for example, with the ball, right? The ball, as it's being released from my hand, has if I'm throwing it up, has a maximum velocity. So once it's released, the second that it's released from my hand, it has the highest, all the energy is transformed into a kinetic energy, okay? So it's 100% kinetic energy. And as it increases in height, so as it goes up, it is therefore decreasing in kinetic energy because it is slowing down, but it's increasing in potential energy. So total energy stays the same, we're just going from one form to another. So if we're looking between two states, the first state might be just that moment at which that ball is released from my hands. That's the initial state, and the final state could be at the top, right where it meets sort of its maximum height before it starts coming back down. Well, at that point, all of the kinetic energy is transformed into potential energy, right? Because we end up with zero velocity at its peak, but it's also at a maximum height, so that is a maximum potential energy. So the activating energy here would be that kinetic energy, and that would be equal to the resulting energy, which would be the potential energy. So how would we do this if we were solving a problem like this? We need to say figure out the maximum height, for example, well, what we would have to do is take those equations for each of those. So what I'm going to do just to show you here is this term right here, this activating energy equal to resulting energy. I want you to write that whenever you're starting a problem like this. I want you to write that equation out. It doesn't mean a whole lot, but it's just sort of a trigger for you to remember, okay, I have to take all of my activating energies or initial energies and make them equal to all of the resulting energies. And it could be multiple forms. In this particular case, when I'm talking about just a ball, okay, so a ball that is starting, say, from my hand, I release it with a certain velocity and it travels up to a maximum height. Okay, so we end up with a height. That's maybe what we want to figure out for this problem. Okay, so in here we have a V0 and we have a V1, right? We have an H and we have the two equations. So for activating energy, that would be my kinetic energy. So it's equal to 1/2 mv. Remember, it's going to be V1 squared minus V0 squared. And then that's equal to the resulting energy, which is just weight, or instead of weight, we can say M. We might know M, G, and H. And so clearly in a problem like this, we would need to have been given the mass and the velocity. And then from there, we can rearrange this equation to solve for H. And we'd be able to determine how high, as long as we know what the initial and final velocity is, we'd be able to determine how high that goes. And in fact, we wouldn't even need to be given the mass if you look at this equation, because there is the mass term on both sides of this equation. So we could technically cancel out each mass term and just rearrange and solve for H. So that in its most basic form is how you would solve these types of problems where you have a change in energy from one type to another. All the questions up to this point, we didn't talk about a change in energy. We just said, well, here's a certain state, something's moving at a certain speed, so that would be a kinetic energy, or something is brought up to a certain height, so that's a potential energy, or something is just moved along a distance, so that would just be your work, right? Now we're talking about actually going from one state to another. So this is a bit of a leap in terms of difficulty, but we're going to kind of work our way up. So what I'm going to do is I'm going to start a new slide here, and we're going to look at question 1437. Okay, so 1437 at the end of the chapter. So that is on page... Okay, so that's page 506. Okay, so 1437 says a 1,200-pound wrecking ball with a velocity of 4 feet per second at the bottom of its arc strikes a wall and comes to rest in a distance of 9 inches. Neglecting any change in height of the ball, determine A, the average force on the wall, B, the deceleration rate, and C, the time period of deceleration. Okay, so the key here first, it's always, again, we want to start with drawing a free body diagram. From there, then we'll do that activating energy equals resulting energy. So we're talking about a wrecking ball. So a wrecking ball would just be something like this, right? Just a circle, big ball. Okay, so it's obviously on some sort of chain, and it states that it is 1,200 pounds, and it strikes a wall right at its bottom of its arc. So if you know that this thing was coming down, say this way, okay, and right at this moment at the bottom of its arc is when it hits a wall. Okay, so here's the wall. We're going to draw in. It says that right at the bottom of its arc, it has a velocity of 4 feet per second. So we know right at this moment of impact here, that's V0. And why I say V0? Because that is the initial state. So that's the first one, 4 feet per second. Okay, so that's the initial state. Now it says from there, it comes to rest in a distance of 9 inches. So this is sort of our state 1, our first state. So maybe I'll write it like that, state 1. Okay, and then let's look at state 2. State 2 would be, it's just we're taking this wrecking ball, and it's just going to go a little further, doesn't it? So it says it comes to rest 9 inches, in 9 inches. Now it does say that it doesn't raise in height. So clearly if this is at the bottom of the arc, it would raise a little bit in height, but I guess that arc is so big, we assume that there's no change in height. It's just a horizontal displacement. We know again that initial velocity, I'll just write it again, v naught is equal to 4 feet per second. And that the final velocity, well, it says it comes to rest. So therefore it must be 0 feet per second. So we'll say then this is state 2. So the second part, or it kind of just is 2 free body diagrams. It shows you the initial, it impacting the wall, and then on the right here, it moving to that final position. So the first thing that it's asking us to determine, so determine A, the average force on the wall. Okay, clearly in this one, so this is where it can be difficult because you might say, well, geez, is it just a simple equation or what? But the fact that there are 2 states give it away, right? There's 2, we're saying we're starting here and we're ending there. And so right off the bat, what you should realize is that we have to use the conservation of energy here. And we're going to do what I said to do every single time you're doing one of these problems, is activating E for energy is equal to resulting energy. And what makes these types of problems difficult is that you can't see the solution. Okay, you don't know what your equation is going to look like just by looking at this problem. I don't even know what it is right now. All I know is that we have an initial state and a final state. So an initial energy and a final energy. And so we're going to put in what we think it might be and try to solve from there. See if we have enough knowns and unknowns. So in terms of the initial energy or activating energy, we have to decide, does it involve springs? No. Okay, so not spring energy. Is it a force over a distance? Well, not really. There's no force given. There is a weight. But what's really gives this one away is that there is a velocity. There's an initial velocity. And so you should assume that our initial state is kinetic because it's still moving at this point, right? Just before it hits that wall, it is actually still moving. So we're going to assume that all the energy in that ball the wrecking ball is in kinetic energy. So kinetic energy is equal to, well, you might think a couple of things here. First of all, you might think, okay, well, the potential energy, right? Potential energy, because it's moving up. But remember that assumption, what's the assumption it says, is that it only moves a horizontal distance. Oh, okay, so if it's only moving a horizontal distance, then no change in potential energy. What else is there? We said no spring, no potential energy. It comes to rest, so clearly no kinetic energy either. So what's left? Just work. So plus work. Work, or that would just be U, right? Okay, so we really only have 2 terms. On the left, we have kinetic energy, and all that kinetic energy is transferred into work, a force times a distance. And it does say, what is the average force on the wall? Okay, so we have to figure out a force anyways. So let's put in the equations for each of these. For kinetic energy, we know it would be 1/2 m v1 squared minus v naught squared. And that's equal to work, which would be force times a distance. So let's go through each of these terms. Do we have a mass? Well, we don't have a mass, but we do have a weight. So yeah, we can solve for that, no problem. Good. Do we have a V1 and a V2? Sure we do. We know V1 is 0, and we have a V2. Or sorry, V1 is 0, and our V naught we have 4 feet per second. Do we have a force? No, but that's what we're solving for. Do we have a displacement? Yeah, the displacement is in that x direction. And so obviously the force we're going to find has to be in that x direction as well. So let's sub in for these values. So 1/2. Well, again, we have 1,200 pounds. So remember, I'll put that up here for weight. Weight is equal to mg. So therefore, our m value is equal to w over g. So we can put that in here. We can say then that 1,200 pounds divided by, remember not 9.81, but 32.2 feet per second. That'd be squared. And then we have a 0 squared minus 4 feet per second. Not squared, 4 feet per second, but we're then squaring that term. Equal to force times, okay, we're given 9 inches, so we would want to convert that 9 inches to feet. So remember, we want 9 inches to feet, 9 inches on the top. That means we're going to have to, well, we want to convert that to feet. We just divide it by 12 inches, right? So 9 inches divided by 12 gives us our feet. So feet, okay? So now we rearrange and solve for F. Okay, so F is equal to, because of that -4 in there, you're going to see that we get negative 398 pounds. And I'm going to highlight that. Now, why did we get a negative value? Well, clearly our velocities to the right are positive, so that must mean then that the force that we determined was to the, probably to the left, right? Okay, that's well, that would be, yeah, it might be a bit confusing because you say, well, wait a second, that negative 398 pounds, how could it be going to the left? This is the average force on the wall. True, but what's happening when you think about that for a second is all of this has to do with the ball, not the wall. And so the force acting on the ball is negative 398 pounds, because that would be Newton's third law. For every force or action, there is an equal and opposite force reaction, right? So we know then that, yes, there's 398 pounds going to the right against the wall. That reactionary force is 398 pounds on the ball. That's why that you get a negative value. That's why that one makes sense, okay? So let's finish this. We still have 2 more questions that it asks. So the next part is B. It wants us to determine the deceleration rate. Clearly it is decelerating because it goes from an initial velocity to a final velocity, right? Go back here, a v naught of 4 feet per second down to 0 feet per second. So our acceleration must be going to the left, again, for the ball, okay? So F, in this case, just F is equal to, very simply, ma, okay? Because we have negative 398 pounds. That's the force acting on the ball. And we do have a mass, because we just want to know what the acceleration is. So F equals ma, 1,200 pounds over 32.2 feet per second squared. And we're going to multiply that by a. So when I divide 398 divided by that 1,200 over 32.2, you get a equal to negative 10.7 feet per second squared. And again, a negative value, just indicating that it is to, it would be to the left. Now, last but not least, it does say for part C, the time period of deceleration. Now, these equations work, so time period of deceleration, these equations work because it is an average force. So an average force, we can do F equals ma. We're talking about a time period deceleration. Well, we have an average force, so that means then that is an average deceleration. So A is equal to V over T. Just a very, very simple equation that we had from our previous chapters. So T then is equal to V over A. So all I did, we'll make that small a, not capital A. I just divided both terms by A multiplied by T, and to get our T value here. So that's just equal to V1 minus V0 over A, which is equal to negative 4 feet per second over negative 10.7 feet per second squared. And as expected, we do get a positive value of 0.375 seconds. Okay, so as long as you had recognized here that the first question, that's really the new problem here, is the activating energy, so the initial energy, and the final energy. How does the energy get transformed from one state to another? And again, it's not to say it's always just going to be one form of energy equaling at one form of energy. It could be multiple forms. So this is probably one of the easier ones in terms of just going from, say, a kinetic to work. We might have both kinetic and potential going to work, or spring and potential going to, something else, to kinetic. So it's just those types of things you have to think about. And then there might be some follow-up ones like this. Okay, so let's move on to our next practice problem. Okay, the next practice problem we're going to look at is 1443 on page 507. So in this problem, there is a block on an incline and there's a spring involved. The spring has a spring constant of 340 newtons per meter, and it's compressed 0.3 meters. If it's released, how far down the slope will the block travel before coming to a stop? So I'm going to draw the setup that we have. So we just have a slope here with a block that's on this slope. And we have a spring that is compressed. Okay, and we know that this block is 4 kilograms. Okay, we know the spring constant K is equal to 340 newtons per meter. We know that it is compressed, X equal to 0.3 meters. And yeah, if it's released from this position, how far down does the block travel before coming to a stop? So in this particular problem, we are missing one more piece of information, and that would be the angle. So the angle inside here is 10 degrees. And it also actually gives us the coefficient of friction here. So mu is equal to 0.8. Okay, so that looks like that's all the information. Determine how far down the block slides before coming to a rest. And it does say in brackets here, spring is not fastened. So it's not connected to block A. And that certainly does make a difference, because you think about that, if that's attached, then when you let this go, as it goes down, all that energy isn't just going into moving that block. A lot of that energy is going into then stretching the spring, right? So you have to think about those two different states. So we have two states. We have one at which The spring, think about that, the spring is compressed, so it has energy it's going to release to push the block, and then it moves down. So we have to determine what it moves into. It says the furthest point it goes. So clearly, yes, it's being converted into kinetic energy because it's moving, but our second state is not while it's moving, it's actually once it's stopped. You could look at potential energy, but here's the problem, is that it stays on that slope, right? So that slope being the baseline. So it's not potential energy, it's not kinetic energy, so we got to think about that. Before we get to that point though, the start of this problem, you should recognize that it would be very similar to what we've done in our previous chapter. What we should do is, first of all, look at the block in a horizontal vertical configuration. And so since we know, I'll just draw it here, that 4 kilogram block has a weight down, that means then that in this view, that weight is like this, right, at an angle of 10 degrees. There is a coefficient of friction, so you know then that clearly there would be force of friction being applied here. So we should probably figure out what that force of friction is. The only way we can do that though is to first figure out, we'll for sure need a vertical component and likely a horizontal component for that weight. So what I'm going to do is I'm just going to set weight equal to mg, and I'll put it in right here. So that's equal to 4 kilograms times 9.81 meters per second squared. So weight is equal to 39.24 newtons. So remember that force of friction is equal to the coefficient of friction times the normal force. So either big N or capital F sub n. Either way, it's the normal force. So there's the only other vertical component, vertical force that's in this picture would be that vertical component from the weight. So we can just put that in directly. So mu is equal to 0.8. And then the normal force would be 39.24 newtons times what? We want the vertical component from this, right? So, oh yeah, so the normal force, oh yeah, okay. I was just looking at one of my answers here and I thought it was sine, that's why it confused me. No, so if it's the vertical component, then clearly that must be cosine 10 degrees. Okay, so 0.8 times 39.24 times cosine 10 degrees gives us, I'll just start over here, gives us that component right there, right? All right, so that would be then equal to, you solve for that, we get 30.9 newtons. So we have a force of friction going to the left, but we also have a force due to the weight going to the right. So what we would need to know is, what is that external unbalanced force? Right? There's no way we can solve any of these types of problems unless we know what that is. We're not going to use the method we did last time where we would involve inertia and all that. We had to do that before. That's not what this one's asking for. We just need to know what the external force would be. And you may not realize that quite yet, but I'm going to do that now, and then I'll remind you why if you didn't realize that right off the bat, why you would probably realize that later on. So what we're really going to do here is we're just going to figure out what the net force is, the net or external unbalanced force. I'm just going to call it the net force. That's just going to be equal to the force of friction minus that horizontal component, which is 39.24 newtons times sine 10 degrees. So that force of friction, remember, is 30.9 newtons, so we are just subtracting 39.24 newtons times sine 10 degrees. And so the net force acting on this block would be 24.9 newtons. Now, I showed it that way, assuming that obviously to the left would be positive, so that net force would be, that net force, if you drew it out that way, you'd say is, hey, that's negative. It actually means that it's going down. And certainly that makes sense, because if the frictional force was higher, then the block would be going up the slope, not down the slope. So that's why I didn't put in the negative value. You could have just switched it. As long as you recognize that, like, I can put that negative value in, and that just means then, oh, I had assumed that to the left was positive. That's why I get the negative value. So that net, I can show it in here as, maybe not yellow, might be hard to see. So this is your F net value going to the right, okay? So we're going to use that now, okay? And like I said, you might not have recognized that right off the bat, how to do that, but you would have realized, hey, there are two states, and Shane said to do what? He said to always write this out. Activating energy is equal to the resulting energy. Okay, so activating, so your initial states equal to your final states. Well, our initial state, remember, is this block. It's not moving, but you have compressed that spring. So as soon as you let that go, all the energy in that spring is being transferred to the block. So the initial energy would be the spring energy. Okay. Now the other side of it, you're going to say, well, it goes down to a stop. Well, as I said, because it goes right to a stop, clearly it can't be kinetic energy. It's not spring energy because the spring's not connected. It's not potential energy because that block is attached to the ground. So the only thing left is work. And that kind of makes sense because there is a force, there's a net force here times a distance. And that's where I say you might have recognized that at this point. If we go, this is equal to F times S. Wait a second. Well, actually, I'll back that up. I'll say where spring energy is equal to work. And I'm just going to put in the equations. So spring energy is 1/2 kx squared, whereas work is a force times a distance. Now, we are supposed to solve for, it says determine how far down the block. So we're going to be solving for S. So we need to know K, which was already given. So we know we have that. X was given. So it's the force that we would need to figure out. So if you didn't do that initially, you would have said, okay, well, which force is it? Well, clearly there's only one force that is actually pushing this block down, and that would be the net force in this case. The weight, but you have to subtract the friction force that's going in the opposite direction there, okay? So we do have force. And we'll, if you want to make it clear, I can even put in F net in this case. So let's sub in our numbers. So 1/2, this is 340 newtons per meter that was given, and 0.3 meters also given, equal to 24.1 newtons, which we calculated, times a total displacement, and that displacement is 0.635 meters. Okay. So again, you might have started with this page right here. Said, okay, Shane said to do this every single time. Activating energy equals resulting energy. Putting the equations, or at least the concepts that make sense. It starts as a spring energy that equals a work energy. Sub in those equations and then figure out what you need. You were given a K, you were given an X, you're solving for S. Okay, there's just F left to figure out. And then you might have went this way and said, okay, I'll draw this free body diagram, figure out which forces are acting on this block. So you might solve this a little bit differently when you're doing it, and that is certainly okay. The order, but you will inevitably need to write this out. Okay, so let's look at one more for today. We're going to look at question 1450 on page 509. I will take a look at a couple more problems and then some review in what will likely be my last video, or I might break it up into two. And I will post information about the final test. For right now, what I would like you guys to do is really just focus on making sure you understand these problems that we're going over right now. And I'll be giving you your fourth and final assignments, and you'll have just over a week to complete that. So without further ado, let's look at 1450. So it says it has a block hanging by a spring. So this spring is attached to the block, and it's just hanging from a ceiling or some sort of mount. So it says if the spring in this problem has a mass 25 kilograms, so the spring is attached to a mass that has 25 kilograms and it's released from the position shown, determine the maximum distance upwards that the mass can move. So no work is done in compressing the spring. So I had mentioned that in the previous example, that if the spring was attached, well, you're compressing it, letting it go, there'd be work in making it in tension. So this would be the opposite. You're pulling it in tension. Some of that work should go into compressing it, but it's actually saying just to ignore it for this particular problem. So that makes our life quite a bit easier. So let's look at the example in question. So we have a spring here, okay, which is attached to a block. And this block is 25 kilograms. And it says that it actually shows that it is at a current displacement here of 1 meter. Okay, so that's the length of the spring at the moment. That being said, if you read the problem, which refers to another problem, it actually says that the free length, okay, so this is really important here. It says the free length of the spring is equal to 0.6 meters. So that means that spring is currently in tension, which makes sense because it wants us to determine the max distance the block moves upwards the max distance that the block moves upwards. And a very important point, so I'll write it down, is assume no work done by compressing spring. Okay, so no work is done by compressing the spring. The other thing clearly that we would need, unless that was something they were asking for, but it's not here, is the value of K. It will obviously have a spring constant, so that K is equal to 1500, and that's newtons per meter. Okay, so first thing, okay, how you should start almost every problem like this is activating energy equal to resulting. So your initial state equal to final state energy. So activating energy equal to resulting energy. So very similar to the last problem, this spring is in tension, and as soon as we let it go, that is our activating energy. We let it go and all of the energy is stored in that spring. So clearly the activating energy is the spring energy. And now it's going from that position and it's moving up. And it wants to know how far it goes upwards. Well, it's obviously going to stop once the velocity is 0. So again, it can't be anything to do with kinetic energy. Like the last problem, you could look at it and say, well, it does go a displacement. We do have to figure that out. And we would need to know the force. So it could be work, it could be, but something else that's closely related to it would be potential energy. right? Because potential energy is a weight. Well, hey, we have our mass, which so we can figure out our weight, and it goes a height. So this is exactly what this one is. It would be spring energy equal to, call it PE for potential energy. So let's put in our equations. So 1/2 kx squared, and that's equal to WH, which is just equal to mgh. So let's look at these. We need to find out what h is. We have m, we have g, we have k. Do we have x? We do, not directly, but we can solve for that, right? X is equal to, it is currently at a state of 1 meter, but its free length is 0.6 meters. So the actual value at which it's compressed, or in this case, not compressed, but elongated, is 0.4 meters. That's what's really key. A lot of people might just put in the 1 meter, in which case you would be wrong, and that's because it's not expanded, it's not stretched out 1 meter, it's actually only stretched 0.4 meters. So you need to know what its free length is. Okay, make sure you have that. Okay, so now we can sub in our values here. So 1/2 K, which is 1500 newtons per meter, times X, which is 0.4 meters. We're going to square that, equal to our mass, which is 25 kilograms, times G, which is 9.81 meters per second squared, times H, and H is what we want to solve for. So you can take the left-hand side, solve for that, then divide it by that 25 times 9.81, gives us an H value of 0.49 meters. Okay, and that's it for that one.